Hello and welcome in our YouTube channel Metallurgical Facts. So in this video series we are doing VIZAG-RINL Management Trainee previous year papers and we are doing 2017 paper. So this is the part 4 of this video series. If you did not watch those three parts, go through the playlist and watch that videos also. Okay, so in this video I have included only 7 questions because I cannot compromise with the discussions. So for reducing the duration of the video, I have taken only 7 questions. So I think you may learn many concepts from these 7 questions from the previous year of VIZAG RNL MT. So now we will see the questions. So the first question of this video is critical stress intensity factor KIC is proportional to. So this here I have written 31 because in previous 3 part I have already did 30 questions. Okay, so this is the first question of this video. So KIC we have already done one numerical on this KIC, its stress intensity factor, and I have already told you everything about that formula. So KIC we can represent KIC is equals to sigma under root of pi c. Okay, so from here what we can observe that this KIC is directly proportional to under root of C. Okay, and in this question they are asking about critical stress intensity factor KIC is proportional to. So we can identify that under root of C is correct answer for this question. So this is the simple question, and in RINL exam they can ask the questions like that. Okay, so we have to be careful while choosing the options. So the next question is the half length of cracks in steel is 2 micron meter, taking Y is equals to 200 giganewton per meter square. So this is Y means E, this is elastic modulus. Estimate the brittle fracture strength at low temperatures. So we have to identify this sigma value if the true surface energy is 1.5 joule per meter square. So this is our gamma value. Okay, so this is something we can relate from brittle fracture. I have already given one video or dedicated to Griffith theory of brittle fracture. So having good idea about the Griffith brittle fracture, you can watch that video from our playlist of mechanical metallurgy. Okay, so I am doing numerical here. So this crack length C is equals to half crack length is given. That means they have given the surface crack length. C is equals to 2 multiplied by 10 to the power 6, and this is in meter. Okay, and this E value or we can say here Y value is 200 giganewton per meter square. So we can write 200 multiplied by 10 to the power 9 newton per meter square. So first we will change the unit conversion. Okay, so this gamma value I am writing here E because we will not confuse with this Y and gamma. That's why I am writing E always. Okay, so gamma is equals to 1.5. This is the terminology problem. 1.5 joule per meter square. So what we know about the Griffith formula, that sigma is equals to under root of 2 e gamma by pi c. Okay, so if we will put the every value in this formula, so 2 multiplied by 200 into 10 to the power 9 multiplied by 1.5 divide pi multiplied by 2 into 10 to the power minus 6. Okay, so what we will get, the value 308.2 something and 10 to the power 7. Okay, so if we will remove this power, so this will be 10 to the power 308.2 into 10 to the power 6. So if we will eliminate this 6, so we can use the suppose this sigma value is 308.2 into 10 to the power 6. So unit for this is now newton per meter square. Okay, so suppose if we will remove this 10 to the power 6, so this will be mega newton per meter square. Okay, so this is 308 means approximate 310. Okay, as per options, so we can choose the D option from this given options. Okay, so D is correct for this question. This is how we did the this question by putting all the values in Griffith formula, and then we got the value of sigma. Okay, so this is the easy question. The next question is total number of slip system in NaCl crystal is. Okay, so they are asking about slip system in NaCl. So we know for FCC the slip system is number of slip system is 12, in BCC 48, in SCP this is important, so you can learn these things. Okay, so this is what I am writing here, slip system, number of slip systems. Okay, And one thing that they also ask the slip plane and slip directions, okay, which is basically which combines and make the slip systems, okay. So for NaCl, number of slip system is 6, so we can learn this thing, okay. And here here they are asking about NaCl, that's why I'm writing for NaCl the slip plane for NaCl is 110 and slip direction for NaCl is 110 also. So these both are the same. This is the slip plane and this is slip direction for uh, NaCl. Okay. So you can verify in from any standard book of for material science. In that book they have given these things. Okay. So for now we can see that a total number of slip system in NaCl crystal is 6. Okay. So 6 is correct answer for this question. Next question is, as we go down a column of periodic table, the elastic modulus. In first part of this video series, I have already told about you the elastic modulus of transition metals and like that I have discussed already. So this elastic modulus basically depends on the covalent nature of bonding, okay, covalent nature of the bonding. So as we go down in any column of the periodic table, this covalent nature of bonding basically decreases, and this depends, and this elastic modulus totally depends on this covalent nature of the bonding, directly proportional to the covalent nature of the bonding. So as covalent nature of the bonding will decrease, the elastic modulus also will decrease. So from here we can say that as we go down a column of the periodic table, the elastic modulus will decrease, okay. So because this is decreasing because the covalent nature of the bonding is also decreasing. So for one of the column, if we will take Si G and some other elements. So if we will go from top to bottom, we'll find that the carbon have the highest elastic modulus, while silicon have some lower value than the carbon, and germanium have some lower value for elastic modulus. Okay, so we can compare like that. So here the correct answer is D part, that is decreases. So the next question is, grain growth occurs in temperature range. So they have given the few temperature range. This is basically how we represent the recrystallization temperatures. Okay, and I will tell you what is the recrystallization temperature for pure metal and impure metal range. Okay, so this grain growth actually refers to the increase in average grain size. Okay, so average grain size will increase. Average grain size I am writing here, that will be clear. If grain growth will take place, so average grain size will increase on further annealing. Okay. After all, what will happen? This happened after all the cold work material has recrystallized. So when once the whole material recrystallizes, this grain growth occurs, and in this grain growth, average grain size increases. Okay. So we know this grain growth. Sorry, this recrystallization temperature range for pure metal is 0.3 tm. That this is for very pure metals, okay. And for impure metals, or you can say for alloys, it is 0.5 to 0.6 tm. So this is for impure metal, okay. So this is the recrystallization temperature, and this grain growth happens once the all recrystallization takes place, okay. So we can say somewhere between 0.6 to 1 tm, or 1 tm means this is basically this reach up to the melting temperature, okay. So as per the options, we can see grain growth only can take place after 0.6 tm, okay. And as per the options, we can see that this 0.4 to 1 tm is one option that favors these things, okay. So this C is the correct answer for this question, okay. And this thing we have to remember that 0.3 tm is very pure metal, and 0.5 to 0.6 tm is for impure metal. And what is this? This is recrystallization temperature, okay. And recrystallization after once the recrystallization of cold material done, then only the grain growth take place, okay. So that's why we can relate from here, and the C option is correct for this question. Next question is, tick the methods that improves fatigue resistance of material. So I have already discussed this question in another form, but here again I will discuss this question. Okay, so we should know about that which factors improve the fatigue resistance and what is the fatigue resistance. Fatigue resistance is basically the increasing the endurance limit of that material. Okay, so one thing is important for fatigue resistance is that good design. Okay, so if good design will be of that component, so fatigue resistance can be improved. Why? Because this in this good design we can avoid the sharp corners, which basically produces the regions for the stress concentrations. Okay, so if the stress concentration regions will not present, so the crack will not take place. Okay, so this is good design is one thing. And for the good design, we can, what we can do the polishing of the surface. Okay, once we will do the polishing of the surface, so what will happen, this polishing of surface will reduce the irregularities on the surface. And this irregularities is basically the responsible for the crack initiation. So once we will do the polishing of the surface, good polishing of the surface, that will be the good surface finish, so that will remove the irregularities. So this is also one method for improving the fatigue resistance. Next is short pinning. In short pinning, what happens, in short pinning we introduce the compressive stresses at the surface, so that compressive stresses also improves the fatigue resistance. Okay, so this is the third thing. Fourth thing is carburizing. We can say the surface hardening, carburizing and nitriding. Basically what happens in carburizing and nitriding, what we introduce a strong surface layer. Okay, so a strong surface layer also resist the crack, and they can also resist the they can also improve the fatigue resistance. Okay, so this is also good for fatigue resistance. So fifth one, we can say the fine grain size also improves the fatigue resistance. Okay, however, for creep we need coarse grain size or single crystal, but in fatigue we need fine grain size for improving its fatigue resistance. Okay, and the most odd thing is decarburization. Sometimes you will get the decarburization in options. Okay, so this decarburization, what happens in this decarburization, basically we remove the carbon, we decarburized. Okay, so by that what we do, we produce a soft material. Okay, we produce a soft surface, we can say soft surface, and that soft surface produces the irregularities, or from that soft surface the crack initiation takes place. So this decarburization is not used for fatigue resistance. So these five things we can use for improving the fatigue resistance. So in this option we can say fine grain size is here, short pinning is here, and pulsing of the surface. So all of the above is correct answer for this question. Okay, so this is the good question, and in any form they can ask this question. And in GATE 2021, in MSQs type of questions, MSQs, you know, this is the new question pattern type introduced in GATE 2021. So this is important for those aspects also. Okay, so this is good question. Next question is statement 1, that is spring represents the perfectly elastic behavior, and the statement 2 says that a dashpot represents a pure viscous behavior. Okay, so these are the options, that is statement 1 is false or true, or the combination of those two statements. Okay, so we will see what is correct for this question, how we choose the options for this question. So first of all, we need to understand this elastic behavior we already know, and this viscous behavior is basically the viscoelastic behavior is found in the materials which responds to an applied stress by both recoverable and permanent deformation, and this is time dependent. Okay, so this is also time dependent, creep is also time dependent, but this happens in organic polymer, in most of the organic polymer and non-crystalline material. However, this creep happens in crystalline material. So we can say that this viscoelastic behavior is basically when we apply the stress, and that can that can be recoverable and permanent deformation both happens at the same time, and this is time dependent. So this is known as viscoelastic behavior. And this is basically, dash spot is basically a mechanical device, a damper we can say, which resists the motion with by viscous friction. Okay, so this was the This was the one of the model of spring dashpot model. We can say spring dashpot model in one of the experiment. Okay, they use these things, and from there, that standard book Raghavan, they have given this question. There is no sense of giving these type of questions in exams. Okay, so we can say only that we can have a general idea about these things, and we can solve this type of questions so by only those things. Okay, there is no concept like that. Okay, so we know this spring represents the perfectly elastic behavior. We already know this is the statement one is correct. So from here we get that this B and C may be correct because statement one is true for this statement only. Okay, so we eliminated is A and D. Okay, so A and D is negative for this, and B and C. Now we will check. A dashpot represents a pure viscous behavior. Okay, so I already told you dashpot is a mechanical device, a damper which reduces the motion by viscous friction. So that have the viscous behavior. So we can say that a dashpot represents a pure viscous behavior. So this is also true. So we can say C option is correct for this question. Okay. Thank you guys for your attention. Hope you guys have learned something new in this video. We will try to add rest of the parts as soon as possible before RINL 2020 exam, and subscribe our channel and press bell icon to get notification for upcoming videos. Thank you.